Okay, so I want to talk a little bit about endurance, cardiovascular health, and I'll cover a little bit about why I don't really like this whole concept of zones that we've come up with so much. They're largely inconsistent, and you're about to see why, but hopefully from this you'll get an understanding of what endurance is, what is happening when we do endurance type of training, what's happening in the body, so that hopefully when you go and do your endurance workouts, you can then modify and adapt it based on the real life principles and the actual happenings of the body. So the first thing I want to point out are there's three ways the body produces energy. Okay, so so I've written down power over here. So we have a certain amount of power output and then how long that power output is sustained. So this first one here is a very quick burst of energy, just like that, but we cannot sustain it for very long. Next up, this blue line is not quite as much power, but over a little duration. We're talking about 60 to 90 seconds. And then last but not least, this black line is a very long sustained power duration that we can hold for a very long period of time, okay? So this red one is what we call anaerobic alactic, this blue one is what we call anaerobic lactic, and this black one is what we call aerobic, okay? So this is largely due to the energy source of that system. So within the aerobic, we're using mainly oxygen and some other substrates or some other fuel sources to make that happen. Whereas this blue one, we're using sugar without so much of the use of oxygen. But that creates a muscular acidosis. The muscle gets more acidic, and another product released from that mechanism is something called lactate. Okay, otherwise known as lactic acid, although maybe not the correct terminology. So if you've ever been to, in fact, I'll come over here and talk about the importance of that aerobic system. So some researchers measured the amount of energy and where the energy was coming from within the body whilst they made them do a few different amounts of exercise. They made them do 200 meter sprint, a 400 meter sprint, 800 meter, 1200 meter. And what we see is this blue zone is anaerobic energy, okay? So that's the blue and the red over here. Anaerobic meaning without oxygen. And in the 200 meters, it's mostly anaerobic, right? 400 meters, it's starting to get half and half, but what we're seeing is that anaerobic hasn't really gone up much. 800, anaerobic hasn't gone up much. 1200 meters, anaerobic hasn't gone up much, but the aerobic has, okay? We hit a wall so quickly with this anaerobic energy because we don't have a lot to pull from. Whereas the aerobic system, the oxygen system, we can keep it going for quite long, sustained periods of time. Okay, so this is hugely vital to our health, and it's something we can measure with our VO2 max, something you might have heard before. Essentially, this is the best measure we have of our cardiovascular health. Okay. The amount of oxygen your body can utilize at a time. And the research shows that people that live long lives and the people that live healthy lives have a nice high VO2 max. So that's something we work on. And if you've ever done any sort of metabolic testing, you've probably received a graph like this that has a certain amount of power output, how long that power output took place, measure of certain gases and bloods and whatnot that were tracked all the way through to see how they changed throughout the test. And then you might have a few points placed on the graph, the last one being that VO2 max. But it is possible to do testing of VO2 max without any sort of metabolic testing. It would be a little less accurate, but is a good way to see where you are. So a few different factors play out into endurance, and essentially if you want to increase your VO2 max, this is a very high level of effort that you can't really sustain for very long. Look, all this stuff then starts to drop off because we cannot sustain it. What we can do is we can push up these 2 points of the graph, and I'll talk about a little bit about what they are in a little bit, but by pushing these up we can shift our VO2 max up. One thing that is quite important to bear in mind is what this graph looks like is going to be quite different for everyone. Some people, these two lines are going to be right near each other. Sometimes they're all going to be pushed right up to the top of that VO2 max. Sometimes they're quite far apart. There's so many different variations of what this graph can look like, just depending on the person and their own genetic circumstance, their own training history. These sort of things will change where we are. So when we, I want to look a little bit about what happens when we do some cardiovascular training, and then maybe about how different types of training will cause different adaptations, and then the different adaptations causing different things in the body to happen, and then that'll lead us to talk about different exercise zones and what different zones do. So a nice simple adaptation of cardiovascular training. We also see this adaptation in resistance training is we have here capillaries, so the veins and the arteries traveling through the body, and the blood travels through these to get to where it wants to be, to the working muscles and whatnot. And in an untrained person, there's not a whole lot of these, okay? And blood has a really tough time getting around. When you do a lot of training, there's more of these pathways for the blood to travel, and then blood can get oxygen to muscles quicker, more efficiently, and then that leads to better muscle usage because they like to use that oxygen to activate. So more capillaries is a good thing. Now, another adaptation of cardiovascular training is in the heart, okay? And the heart is such a hugely important organ, but how you train it has some significant impacts to what happens. If you do a lot of resistance training in the gym, it's not necessarily a good adaptation of the heart for endurance type stuff. Essentially, when you do a lot of resistance training, you're putting a lot of strain on the body, and that is increasing the blood pressure, and then increased blood pressure is going to thicken up these heart walls, and those thicker heart walls creates less space in the heart cavity, so it can't stretch so much. And then this, thick heart is less mobile, less able to contract. So a lot of people say just lift weights, that'll be your cardio. If that was true, then all the big powerlifters, all the weightlifters have super high VO2 maxes, right? But they don't, right? That's the fact of the matter, because this increased blood pressure, this thick heart wall is not good for your cardiovascular health so much. So what happens is when you're just at rest, your heart is filling maybe halfway with blood, and it's not really causing stretch, and it contracts. We're not putting any demand on the body for oxygen, so there's no need to deliver it. When we train really, really, really super hard, and we cause that heart to beat super fast, right, and it's beating really, really, really fast, it's not filling up all the way with blood either, because as soon as there's a little bit of blood in there, it's pumped out, because we're putting that much oxygen, demand for oxygen, that the body's really pumping fast. Whereas when we train at a slightly elevated heart rate, what we're doing is we're putting enough demand on the body to fill the heart up all the way with blood, because it wants to stretch, fill up the oxygen. So we're getting a nice big stretch in the heart cavity before it contracts. And then it's stretching from a contracted point, and that creates strength, but also space within the heart cavity, and the more blood that can fill up there, okay? So there's two components of the strength of your heart. So we call it cardiac output, I'll put CO, and that is equal to stroke volume times heart rate. So cardiac output, the strength of your heart, is equal to the stroke volume. So the stroke volume is how hard your heart is beating on each beat. So having a nice stretchy heart cavity that can beat hard is going to increase your stroke volume. And your heart rate is how fast your heart is beating. Okay. Now, this training on this side of the aspect is more along the lines of being able to maintain high heart rates for longer. What we do see in very elite athletes is even at higher heart rates, they still have a high stroke volume. The heart is still beating quite strong. That's not going to be the same for most people, unfortunately. But how we sustain high heart rates is by having a lot of mitochondria in the heart, which we're going to talk about next. And mitochondria are also within the muscles. So should I talk about mitochondria next, or should I go into how the muscles work? I think I'm going to how the muscles work, and then everything else will make a lot more sense. So you have 3 types of muscle. You have type 1 muscle. This is very aerobic muscle. It's built to endure, but it's not built to be strong. So these are built for long bouts of exercise, and they use oxygen mainly as their fuel source. They like to use oxygen and then burn that with another substrate. Maybe that's a fat, maybe that's a carbohydrate. Then at the other end of the spectrum are your type 2B fibers. These are your strong fibers. They produce a lot of strong, powerful energy, but they're not very enduring. And they run out of gas very quick. And then in the middle is your type 2A fibers, also sometimes referred to as adaptive fibers, because they can go either way depending on how you train. If you train a lot of aerobic work, they'll look more like the aerobic fibers. If you're training a lot of strength work, they'll look more like the type 2B fibers. Okay? And so this little cell here is what activates these fibers, okay? Or what we call a motor unit is the brain telling the muscle fibers to work. And within a muscle, you have multiple fibers, all these fibers here, and one motor unit contracts one fiber. So if only one unit comes off, maybe this fiber fires, nothing else. And this fiber fires in its entirety, whereas if 2 go off, then another one will go, 2 motor units, 2 fibers, 3 and 3, and so on. And we often measure this in percentages. What percentage of your muscle fibers are you using at a given time? Now, this is important because the signals in the body is all electricity, and we need to put more potential into the body to activate some muscle fibers more than others, or activate some more motor units more than others. Some are more resistant. So your type 1 fibers are typically recruited by what we call low threshold motor units, the ones that activate quite easily and quite quickly. They don't need a lot of exercise intensity to be working, whereas the type 2B fibers need quite a lot of electrical stimulation to wake up and then fire those fibers. Okay, so if you want to fire all these fibers here, we need to put a lot of effort. It needs to be it needs to be a powerful exercise for that to happen. Okay, so how is energy being produced in these muscle fibers? So if we go back to this graph over here, there's aerobic energy and anaerobic energy. So the black is anaerobic, the blue and the red are the 2 anaerobic types, the types that don't use oxygen. Now, the cells or the organelles, so we have a cell here of the body, right? And within the cell we have these little red lines called your mitochondria. They're an organelle, is the correct terminology. And these organelles are what that use oxygen and turn it into energy. And what we see is we have 2 muscles here, the type 1 fiber and the type 2 fiber. The type 1 fiber has loads and loads and loads and loads of mitochondria. The type 2 fiber, not so much. Okay. Now, because the type 1 fiber has all these mitochondria, they have a lot of ability to use oxygen as a fuel source. These type 2 fibers, not so much. So they're using a lot of sugar, and creatine phosphate would be the correct terminology here. So that is the working of the muscle fibers. Okay, so should we talk about lactate? So we can increase the number of mitochondria in this type 2B muscle fiber. Okay, and then that will increase our endurance abilities, not only because we have more muscle fibers here, but the byproduct of this energy metabolism is lactate. Okay, which isn't the villain it's made out to be, because then that lactate works with the type 1 fiber, and it goes, all this byproduct lactate, it can't be used in the fiber because there's not enough mitochondria for it. So it gets shuttled to the type 1 fiber, and there's all these mitochondria who now can use that lactate as their energy source. Okay, but for that to make a little more sense, I need to talk about how the body produces energy. Okay, so particularly anaerobic energy, or this blue line over here. So essentially turn sugar or a carbohydrate into energy, and there's two byproducts. Okay, we used to think there was something called lactic acid. A lot of people still refer to lactic acid. Has yet to been found in the human body. Okay, but what we do get is two things: lactate and the hydrogen ion. Okay, the hydrogen ion does make the body more acidic. Okay, this is why this is muscle acidosis. The more hydrogen there is in a muscle, the more acidic it is. Whereas the lactate is then a byproduct of this system that, like I said, can also be used to make energy, particularly by the mitochondria. So it's using that lactate plus oxygen to make that happen. So the body is really efficient in that respect. But it can also use sugar, it can also use fat as well in the mitochondria. So that kind of goes to this graph I've drawn over here. So we have an amount of power, and the power increases at the bottom of this graph, and what the body is using as a fuel source as we change the power of a workout. Okay, so if we're not doing much, we're using some fat as fuel, we're using some carbohydrate as fuel. As we turn up the intensity, we bring up the amount of fat that is being burned as fuel quite significantly, because we're putting that demand on the body, whereas that carbohydrate is steadily rising. After a certain point, however, what happens is because it takes longer for the body to burn fat, it has to break it down first. We're turning up the intensity, so it doesn't have time to turn down the fat. What it does is it shuts off the ability for the mitochondria to take in fat as a fuel source, and it uses everything else. Things such as lactate, which, like I said, are getting funneled in from the type 2B fibers if we're doing high intensity work. But we need to activate those high threshold motor units, the muscle fibers that take a lot of effort to be activating that muscle. So that goes a little bit into training zones, that's a higher training zone. So, and then what happens, because it's shut off fat, is we start to see this dip. So it gets to a point where the body is no longer using fat as a fuel source. It's too inefficient. So now we're relying entirely on the glucose, or the carbohydrates. So that is all well and good so far. So why are mitochondria so special? They have a huge relationship with high VO2 max, and with a huge nice life longevity, nice long life as well. So there's 3 cells here within the body, and then, like I said, they're organelles, they're things that live within a cell, okay? All the mitochondria. So in a young person, we have a cell, a nucleus, and then these mitochondria that move around and produce energy for that cell to use, for that cell's mechanisms to work. And then by the byproduct of that is you can use your body, your heart beats, your lungs expand, your organs do their thing. Now what we see in an old person is a lot of these mitochondria have died off and they've fragmented. And these are really weak, inefficient mitochondria. And that is not good, because the body's not producing energy properly. It also, mitochondria are related to some other processes in the body as well. Whereas people that live to over 100 years old, so they're not just old, they've lived to the upper echelons of life. And what we see is hyperfused mitochondria. So these mitochondria have stuck together, and that has increased their surface area, and then increased surface area means better energy production. So how this works is there's a number of mitochondria in the body, and some of them are a bit rubbish. So what the body does is the rubbish one it flushes out, and it recycles them until they become good. Whereas it also keeps the good ones around, of course, and then when those good ones stay around, you do lots of good exercise, they start to fuse together, that hyperfusion, and then over years and years and years of good training and low stress, you get these nice big chains of mitochondria that are very efficient. Now, a huge part of this is stress. Okay, stress kills the mitochondria. It's part of this process here, so it is necessary to an extent, and that's due to free radicals. So we have an atom here, and then a little electron has escaped. Okay, there's various ways this happens within the body, but this little electron escapes and it does damage. And like I said, it's okay because it's part of the process. The problem happens when there's way too many of these little free radicals floating around the body, and they just start killing. When there's too many of them, they start killing off the ones that are actually good. Okay, and then that decreases our aerobic ability. So that's when you work out a little too intensely, and this is why we should often do lots of a high volume of low intensity exercise, especially when it comes to cardiovascular health. You want to do the type of training that encourages this growth without encouraging this to turn up and do all the damage. If you ask these people, the centurions, their secret to a long life, most of them will tell you one thing, and it's a low stress life. And that's quite significant because this stuff right here, this free radical, has a huge relationship with stress. Okay? We know that stress kills off the mitochondria, increases the number of free radicals, which are doing a lot of damage within the body. So low stress is important in that respect. Now, these graphs are indeed quite interesting because when it comes to training zones, so I've covered the importance of like why you should train hard, so that we can get more mitochondria in the heart for that long duration heart beating, or we need more mitochondria in the type 2 muscle fibers, because then it creates more lactate to shuttle off to the type 1 fibers, so those mitochondria can use that, but then that requires high threshold energy, so that means more powerful in the exercise, which means a higher training zone, and so on. So what is interesting is we have VO2 max here, but this can also be measured in terms of heart rate. So sometimes people look at training zones and say, oh, I need to work at this percentage of my VO2 max. Sometimes you need to work at this percentage of my heart rate. Sometimes this amount of power that I need to work at. So that's a layer of confusion there. Not to mention that what these two graphs here represent is slightly different. What we're seeing on this graph, so this is what we would call fat max, okay? Where we're burning the most fat possible within the body, right? Whereas I haven't even talked about aerobic and anaerobic threshold yet, but aerobic threshold is the point at which we're starting to see an increase in lactate in the body. So when we exercise, right, and that process of turning sugar into energy, we see lactate. And lactate is always being made in the body, just even when you're at rest, just by daily life exercise. But when we start to see an increase in that lactate is what we call the aerobic threshold, okay? So we then get to a point in exercise, so we have here this graph. So as we increase power of an exercise, the heart rate goes up, okay? The more intense we're working, the harder the heart has to beat. And then at a certain point within that, right, the body is no longer able to clear all the lactate out in its entirety, and then there's this build-up of lactate that is building, and we just cannot clear it out, right? And part of the ability to clear it out is, you know, this good relationship here, lots of mitochondria in both muscle types. But as the lactate increases, we get to a point where it cannot get rid of the lactate, so this lactate is building up. Now the lactate, like I said, is not a bad thing, but the hydrogen ion, maybe it is, maybe it's related to other factors related to this that is causing that muscular fatigue. I think the science is a little bit all over the place. I don't think they're 100% sure on what is causing the fatigue, but we do know that we can measure lactate and find out where our fatigue is, even though that lactate is a good thing. So the point at which we can no longer flush out that lactate enzyme. It's called your anaerobic threshold, or this point over here. Okay, so that's that high buildup of lactate. So the reason I bring this up is because this point here, your aerobic threshold, when we're starting to see the lactate levels rise in the blood, is oftentimes going to be around the same point as that fat max, where we're using the most fat as fuel. I believe this aerobic threshold is going to be a little bit further ahead. Whereas then we have, different points in this graph where this goes low over here, whereas we have, so when your body has stopped creating fat, whereas over here when your anaerobic threshold has not been able to clear out that lactate. So when people are saying, oh, I'm training at this percentage of my heart rate, what is happening is some people are talking about these zones here, your aerobic and your anaerobic. Some people are talking about these zones here, based on your fuel usage within the body. So really, what is it we're trying to measure? Okay, and they don't tell you this stuff often.